Hello everybody, and welcome to the continuation of Example 2, which started on page 110. We are going to start on page 111, and just a reminder that what we've already done in this example is to start with a function that was defined like this. Okay, a of x is the integral from -1 to x of f of t dt, and to use that definition to figure out these points and then to plot them up here. Okay, so what our ultimate goal at the end of this example is to get an accurate graph of a of x. Okay, we can do that by kind of working our way through these questions. So let's start with part C here. They ask us, on what intervals should the function a of x be increasing or decreasing? Okay, now it's going to be helpful as we go through this to remind ourselves of the relationship between f and a. Okay, so this function f of x in the upper left, remember that that's the derivative of a. Okay, so with that in mind, as we try to answer this question of where a of x is increasing, we could remind ourselves that a function is increasing where its derivative is positive. In other words, above the x-axis. Okay, so going to the graph of a prime of x, which is the one on the left here, we're just asking, where is that graph above the x-axis? Okay, well, I'm going to highlight the part that's above. Notice that this stretch from -1 to 1.5 we're above, and then again from 4 to 7, there's another stretch that's above. So those two intervals should be the intervals where a of x is increasing. 0 to 1.5 and 4 to 7. Okay, and then similarly, a of x is going to be decreasing on intervals where the derivative is negative, okay, where a prime of x is negative. So back up to our graph, notice that we're below the x-axis from here to here, and that interval, let's see, it starts at 1.5 and ends at 4, so 1.5 to 4. Okay, so we have a little information then about what ultimately this graph of a of x should look like. Okay, and next question asks us to provide a little bit more information. Okay, so at what points does a of x have a local maximum, and at what points does it have a local minimum? Okay, so let's pick one of them. Let's start with this question of a local maximum. Okay, remember what a local maximum on a function looks like. If we draw kind of a little snippet of our function a of x, a local maximum would kind of have this sort of a shape to it. Okay, and what you might notice is how the derivative is behaving on either side of that local max. So over to the left, our function's increasing, which means the derivative is positive, and over to the right, the function's decreasing, so the derivative is negative. So we could describe that local maximum by noticing that the derivative is positive to the left and negative to the right. Okay, so let's start that statement here. Has a local max at, and we are looking for a point where a prime changes from positive to negative. Okay, so we're going to scroll back up and look at our graph of f and see if we can find a point like that. Okay, so above the x-axis to below the x-axis, notice that this point right here fits that description. Okay, the part of the graph to the left is above, the part of the graph to the right is below. So it would appear then that x equals 1.5 should be a place where a has a local maximum. Okay, and for a local minimum, it's exactly the other way around. Okay, that would be a place where a prime changes from negative to positive. Okay, looking back at the graph in the upper left, are there any points that fit that description? Okay, where a prime of x goes from below the x-axis to above it, and this point right here appears to fit that description, and that's x equals 4. Okay, so a of x is going to have a local minimum then at x equals 4. Okay, so we're kind of piece by piece gathering information about what this graph of a of x should look like. Let's continue. Okay, so the next part of this is asking us about concavity. Okay, and just to warn you, we're going to probably have to do some scrolling up and down here because our graphs are sort of off the page at this point. Okay, so let's think about the concavity part of this first. Okay, so you might remember that a function is concave up where its second derivative is positive and concave down where its second derivative is negative. This presents a little bit of a challenge because we don't have a graph of the second derivative of a, and yet we need to figure out where the second derivative is positive and negative. Okay, so it helps to remember a little relationship between the first and the second derivative here. I'm going to just kind of write it in the margin. Okay, so the second derivative of a function is positive if the first derivative is increasing. Now, one way to think about that is to sort of think about it the other way around. If the first derivative of a function is increasing, then its derivative is positive. That's where this second derivative positive comes from. Okay, so in a nutshell, we can answer this question of where a of x is concave up by just looking for places where the derivative is increasing. Okay, hold that thought. We're going to scroll up to the graph of f again. Okay, I'm going to just get rid of a little bit of the clutter here. And we are looking for places where that a prime of x graph is increasing, where it's going up. Okay, notice that one such interval would be right here from x equals 0 to x equals 1. And then another one is from 2 to 6, it looks like. There the graph of a prime is also increasing. So 0 to 1 and 2 to 6 appear to be our intervals. All right, and then concave down, exactly the other way around. Okay, so we are looking for places where a prime is decreasing. Okay, so we'll scroll back up and see if we can find some intervals that fit that description. Okay, so let's see. A prime is going down from here to here. That appears to be from 1 to 2. Okay, I think that's the only place where our function is decreasing. Okay, so from 1 to 2. Okay, so we have a lot of information now about a of x that should help us to draw the graph of a of x. There's one piece of information that I'd like to add to that, though, that might round it out. Okay, so this kind of goes back to observation that we made in part D, this one that I'm putting an arrow by. A of x has a local max at x equals 1.5. Now, the thing about 1.5 is that it doesn't appear on the table up here. We kind of jump from 1 to 2. And it would be nice to know what the value of our function is at 1.5, right at that local max. So I'd like to take a minute to figure that out, just to add that to our chart of data here. Okay, and we can calculate a of 1.5 by kind of first going back to the definition of what that is. We calculate that by taking an integral. Okay, this is how we defined our function. And to get a number for this, one way to do it is to break this calculation up into two parts. So we could first integrate from -1 to 1, and then integrate from 1 to 1.5. Now the reason for doing that is that this first number here, we already calculated. That's just the value of our function at 1. Okay, we can look at our table and actually see what that number is. A of 1 is just 1. Okay, so we'll start there. What we need to figure out then is the value of the second integral, okay, the integral from 1 to 1.5 of f of t dt. Okay, and to do that, we need to think about areas. So, sorry again for all the scrolling here, but we're going to need to go back up to the graph of f, okay, and that's this one. And we're interested in the amount of area that we get between 1 and 1.5. Okay, let's clear a little clutter away. So we are interested then in this triangle of area right here. Okay, so take a look at that triangle and you might notice that its base is 0.5 and its height is 2. So we can use the 1/2 base times height formula. And we're going to get 1/2 times 0.5 times 2. And if we do that calculation, we're going to get 1 plus a half, which is just 1.5. Okay, so what we've managed to figure out then is that there's another point on this graph. It has an x and a y coordinate of 1.5. Let's go ahead and plot that. Okay, so 1.5 and 1.5 would be there. Okay, I think we are ready to draw here. So, kind of starting way over at the left here at -1, notice that between -1 and 0 on our graph, we don't have any area, so that's telling us that our a of x graph is just going to stay flat there. Okay, and then we're sitting here at x equals 0, and I'd call your attention to the fact that one of the things that we said is that a of x should be concave up between 0 and 1, which means that our graph should sort of have kind of a bowl upward shape between 0 and 1. So that means that when we draw this stretch of graph between here and here, we're going to draw it kind of in a bowl upward shape, kind of like that. We know that it has to have that shape. Okay, and then for the next stretch, we might notice that we also concluded that a of x is concave down from 1 to 2. So we know that it has to have a bowl downward shape on that interval. Okay, so between 1 and 2, concavity is going to kind of flip around and maybe look something like that. Okay, and then the next thing that we could notice is, okay, back to the concavity here. Okay, here it is. So between 2 and 6, we're also concave up. So all the way from 2 to 6 on our graph, we're going to have, whoops, let me try to be consistent with my colors here and stay with blue. So all the way from 2 here to 6 here, we know that we have a bowl upward shape. Okay, so I'm going to do my best to draw that in. And then finally, what's going on between 6 and 7? Okay, well, if you look down at our concavity, the interval from 6 to 7 doesn't appear anywhere. And so what that means is that our graph is neither concave up nor concave down between 6 and 7. And if we're not concave up and we're not concave down, the only possibility is that we're linear. We got to be a straight line. And so that tells us that this very last stretch of the graph should be straight. Okay, and there it is. That is our best estimate of what a of x should look like. I would encourage you to go back and just look at this graph and convince yourself, okay, based on all of the information that we have, that we drew that correctly.